Our next presentation is a triple header from the folks at Montana Tech. Ron White, Director for the Center of Advanced Material Processing, and John Medish, who's the State Geologist with the Bureau of Mines and Geology, and Jerry Downey, who is also at Tech, Head of the Metallurgical and Materials Engineering at Montana Tech. So without further ado, Ron?
Thank you. Well, good morning. I'd like to compliment the organizers of this conference for having a very interesting first day. The historical information and the way that it was presented was really set the tone for where this conference has come from. And to some extent, it looks out into the future. And that's what we're going to do in this presentation. We're going to look out into the future. The program that the three of us are going to talk about, having to do with rare earths, is a program that will only be really initiated this fall, starting with the fall semester in August. And so this is the first time we've spoken publicly about the activity that we're about to undergo. And I think that one of the things that this type of program is going to do is going to lead us into some interesting discussions for the second 30 years of this conference. I'm the director of a center called CAMP. It's a Center for Advanced Materials Processing. And some of you will know this center because we have a wide variety of instrumentation that some of you have utilized to analyze samples with our instrumentation. We do what I guess one could call like a sales and service work for external clients as well as for internal. But CAMP itself is more than just the laboratories that we have at Tech. It's also about the entire educational system at Tech. We participate vigorously now in many aspects of Tech's world, including the management of large research programs. The program we'll talk about today is a new program like that. We've had a similar program for the last 8 years in materials science, also with the Army Research Laboratory. And so this is our second cooperative agreement with them, and will kind of lead us into some interesting new territory. What's my job? My job is basically to keep the train on the tracks. And with these two research programs and with our sales and service activity and with all the other things we're doing, I'm called upon now and again to push the train back as it tries to roll off. I don't need to say very much about rare earths. If you have any interest in them, you know probably more than I do. You know, of course, they're not rare. Some of the rare earths are no rarer than copper and tin on the Earth's surface. They're called earths because of the nomenclature in the late 18th century that classified rocks that dissolved in acid as earths. So they're neither rare, and earths is just a happenstance. What they are, of course, are the elements in the lanthanide series. They are part of what's called the critical minerals. And what is certainly true is that these elements have become an essential component of our culture. And it's partially due to the activities that are shown on this chart, where you can see that rising from physics to, I'll call it today's products, takes us through chemistry, materials, and engineering. And if you look around, not only here, but also within the military, you find that the rare earths and some of the other critical minerals are embedded in today's culture, and we would not like to live without them. One of the problems, of course, is that, there really are two problems connected with the rare earths. One is that the supply chain for them doesn't run through our hands, it runs through the hands of other countries. And for the military, this is a serious issue because we can't predict the future. We never have been able to predict the future, and there's no reason that'll change in the near term. And so we have to backstop our supply chain in some way. And this is going to take some time. This is not something that's going to happen because somebody flicks a switch somewhere, no matter where it is. It has to evolve, and this research program is part of that evolution. There really are two problems. One is that we're sorely lacking data on where the rare earths are in this country. Now we have hints, we have people that have spotted rare earths when they've analyzed samples and components from other things, but we don't have a good understanding of rare earth distribution among things that are often talked about as sources of rare earths, tailings, various kinds of coal waste and whatnot. Well, we need to fix that problem. And so one of the components that Dr. Medish will talk about is an exploration component that's designed to go out in Montana and discover where it is likely that we can find rare earths and at what level is it economically feasible to mine for these materials. And the second thing is that the rare earths are put into the lanthanide series for a very good reason. If you know any chemistry, that's because their properties are all very, very similar. They are, and the other thing that goes with that is that the rare earths don't generally appear alone in samples. They appear in a mixed product. And therefore, you have to take chemically similar entities and separate them. And that takes special techniques. And so the other part of our program that Dr. Downey will talk about is new techniques to separate rare earths and to produce them in an economic and benign, economically feasible and environmentally benign way. So with that, I'm going to turn things over to John Medish, who will tell you about part of the program.
Well, thank you, Ron. Yeah, I'm going to walk through some of the programs. We've got about 7 projects on the Bureau side of things, but really it's a collection of researchers from the Bureau of Mines and Montana Tech to address some of these exploration and quantification issues. So I'll start walking through each one of these projects and give you an idea of what we're going to be working on for the next several years. So the map shows what's referred to as the Montana-Idaho alkalic belt. If you can see the generalized gray area there, that's just occurrence of these igneous intrusives actually extend from Lemhi Pass in Idaho, west corner of the state there on up into Alberta, actually goes up into the Yukon. And that belt is fairly well known for at least having some occurrences of rare earth elements throughout the belt. But as Ron described, they're described as incidental to other deposits and things like that. So the first project then will be led by Chris Gammons, and basically mapping and sampling detailed mineralogical and geochemical analyses of some of these areas. And then we list the 4 or 5 specific areas that they'll be working. So these, we're going to be doing some mapping, doing extensive sampling of these deposits and occurrences to get a sense for what the rare earth concentrations are going to be. The next map here is the coal resources in Montana. They range from lignite down to bituminous. We've got 5 major basins in the state. And so this project will be led by Jay Gunderson with our Billings office. Again, the idea here is to do some detailed sampling of coal beds, but also the interburden and waste products from coal mining and coal processing. North Dakota has shown some really good promising results for the Williston Basin coal in North Dakota. Powder River, some exploration in that in Wyoming, but by and large, not very much rare earth sampling has been done in Montana at all. So we've got 5 areas that we'll be looking for that. The next map here shows a combination of abandoned inactive mines in Montana, something that we're all fairly familiar with. Those are the red dots. Over the top of that is the green areas is generally zones in Montana that have been identified as either high or moderate potential for mineral development. And this is a compilation of work done by USGS, US Bureau of Mines, and the Montana Bureau of Mines over the last 30, 40 years. So what we're going to be looking at for this project will be led by Caleb Scarberry with the Bureau. And again, we're looking at these mines and mine openings as an opportunity to look at the ore body. We've done a lot of environmental work. We have a good sound AIM database, as we've called it, that we gathered in the late 90s into 2000 for BLM and forest. And so we're going to revisit some of these sites that show promise, give us an insight into the ore bodies, and look at a rare earth and critical mineral deposit. So he's broken it up into really 4 areas, but principally starting the first year is to put a lot of this data back together and put it in a rare earth element critical commodities database. The next map shows Montana is part of what's referred to as the Great Permian Basin Phosphoria Formation. If you remember, 30, 40 years ago, phosphate was a very popular product for soaps and things like that. It's fallen out of favor. But even then, when they were doing some of this exploration, actinides and various rare earth elements were mentioned in the literature. So Idaho has produced minor amounts of rare earth elements in some of their phosphoria. So we're going to be looking at kind of the same thing. This will be led by Adrian Van Rijthoven, new economic geologist at the Bureau. Basically, again, just doing the mapping and sampling of the phosphoria formation throughout Montana. We've broken it up into 11 mining districts, going through and basically just going layer by layer through the sedimentary sequence of the phosphoria, sampling and mapping and doing sample sections for that. The next map here shows a lot. This is a combination of everything. And obviously a lot of past producers in Montana, not for rare earths or critical minerals, but for base metals and precious metals. And so the next project in line is going to be led by Ted Duane and Gary Icapini with the Bureau, going back to look at some of the larger waste piles, either tailings, waste rock, mine discharge, and going back and looking through the waste sources and doing essentially prospecting for rare earth elements in there. So we've broken it down into 3 groups: metal mining, processing, of course, phosphate. If you're familiar with Rome Polank out here west of Butte, and acid coal mine data, drainage, especially from the central Montana coal mine. So those are 3 areas that they'll be looking at. The next 2, so those 5 are all really aimed at sampling known resources for rare earth elements. The last 2 projects that I want to describe are related to how we detect some of these things and how we're going to sample these. So what I'm showing here, again, Montana, Idaho alkalic belts, the central Montana alkalic province. Again, very high likelihood of some rare earth elements. So Xiaobing Zhao with Montana Tech, co-PI Chris Gammons are going to be developing new technologies, remote sensing, UAS surveys, using hyperspectral imaging and those kinds of things for some of these areas. The rectangles on there show some of the study areas that Xiaobing will be looking at. So again, we'll be doing some ground sampling, ground truthing, and then Xiaobing will be doing some remote sensing as well. So, and then the last one here, again, abandoned mines, again, past producers, Abby, Cloudberry, Chris Roos, and Thomas Cam with Montana Tech Mining Engineering Department is 2 components of their studies. One will be to be looking at and researching selecting commercial autonomous vehicles that can be suitable for examining hazardous areas. Apparently sending graduate students into old mines is frowned upon now. So they didn't tell me that 30 years ago. So they'll be looking at some of the remote sampling, especially some of these coal mines that have extensive workings and things like that. So that's part 1. The second part will be as we start developing data on some of these sites, the first 5 projects. Of course, the question is going to be, are they economically viable? Are the deposits large enough, concentration? So we're going to use their expertise to help guide that evaluation. So that's pretty much what we'll be doing over the next several years here. So with that, I'll turn it over to Jerry.
Well, good morning, everyone. Pleased to be here with you this morning. In case you weren't paying attention, I'm Jerry Downey. I'm the professor and department head of metallurgical and materials engineering at Montana Tech, and I also double as the director of the materials science PhD program there. Before I get started, I think Ron and John did a great job of laying the groundwork. Every graduate student I've had that's worked on rare earths, the first thing that comes out of their mouth is, no, they're not really rare. But from the metallurgical standpoint, whether you're talking about a primary resource, an ore or a concentrate or a recycled material, they present particular metallurgical challenges. And I'll maybe address that as I start working my way through the presentation here. Essentially what we have is another 7 tasks, okay? And each one of these tasks is predominantly conceptual at this point, although in some cases we've laid the groundwork with some preliminary test work, and in a couple of cases a more extensive series of experiments and pilot work, as a matter of fact. So these aren't shots in the dark, but again, it's high risk, high reward research that we're talking about here. So one of the situations, rare earths, again, coal ash has been mentioned as a rare earth resource, and in fact it is. Rare earths do occur in coal, and once the coal is combusted, the rare earths don't go anywhere. They stay in the condensed state, so they're actually concentrated. The concentration ratio is roughly about 10-to-1, which is actually good. It helps us as metallurgical engineers to have that additional concentration in our starting material. What the problem is, of course, is that the concentrations are still quite low. It says highs of up to 5,000 parts per million, but maybe something on the order of 500 might be a more realistic number. And then you've got other unusual constituents and morphologies in the coal ash that you have to deal with. So the approach that my colleagues, Dr. Young and Dr. Wong, have taken for this particular task is they plan to develop an aggressive leach extraction, elution, precipitation method to separate the rare earth elements from the coal. And naturally, and I won't go through this on every one of our tasks, but characterization is the key. If we can understand how the rare earths occur before we even get started in the laboratory, we can get an idea of what the most effective treatment methods are going to be. Once that happens, then we go to work in the laboratory, optimize relevant reaction mechanisms. Typically, everything that we do within our department, and specifically my research group, is based on a statistically validated design of experiments, which gives us a great deal of confidence in our results. And again, I won't say this for every one of these tasks, but the ultimate goal, the holy grail, is to be able to construct and operate a pilot plant near the end of the conclusion of this project, optimize performance and efficiency, and also gather design criteria for a commercial plant. Okay, the second one of these tasks is actually one of mine, and this is for an integrated pyrometallurgical process for producing high purity rare earth elements from both primary and secondary materials feedstock. The situation is, I mean, currently we know how to extract rare earth elements, but it's a labyrinth of physical separation, hydrometallurgical operations, some pyrometallurgical operations, and to be quite candid, it doesn't work that well. I mean, the physical beneficiation typically has low recoveries, same with the hydrometallurgical, so you just multiply those factors, and by the end of the day, you're lucky to get half of the material that was in the ground out as rare earth products. Pyrometallurgy is a little bit more forgiving. And so what I've conceived is a 5-step pyrometallurgical process that if every step is successful, we'll not only be able to recover the rare earths at a much higher efficiency, but we'll also be able to separate them. And I'm not going to tell you exactly how, because if I can do that, it's going to be of great interest to the Defense Department and the Army Research Laboratory in particular. So anyway, it's a 5-step process. I can tell you that the first step with prior work, some of the work we've already done with the Army, works very, very well. Basically what it's a chlorinating roast, and we're able to leach and extract rare earth elements at an efficiency of 90%. We've proven that with surrogate materials and also with actual ore and concentrate samples. Okay, so the next project is also, the PI is again Dr. Courtney Young, and the co-PI is Richard Leducer, who works in the mechanical engineering department at Montana Tech. And their idea is for advanced processing of rare earth elements by flotation process. So as I think Ron said a little bit earlier, rare earths typically contain more than one mineral, multiple rare earth elements. It's a very complex mineralogical problem, and that's why the concentration effectiveness is typically so low. Well, the idea that Courtney and Rick have come up with is to take a look at using suites of REE-specific collectors. Instead of hoping to collect all of the rare earth elements with just one collector, their plan is to have collectors that are specific to every rare earth element in the particular mineral deposit that they're looking at. So again, if they do this, they're going to go ahead, hopefully identify high efficiency collectors. They'll go through this same statistical evaluation that I mentioned before, develop computational models. And if everything pans out perfectly, then they'll be evaluating traditional mechanical flotation and also column flotation. Okay, the next project is number 11 is again one of mine, and I'll be working with Grant Wallace, who's a research associate that works with my research group. And the idea here is selective separation of rare earth elements from an aqueous solution using what we call a continuous flow metal recovery system. Okay, this will actually be the third project that I've had funded for this system. Earlier, I had one through the state of Montana, the Moretti program, and I'm currently working on a National Science Foundation grant. So this continuous flow metal reactor system works really well. Basically, and try and go really quickly here, we have particles that are either magnetite or magnetite that's been coated with silica or some other coating, and then have functionalized molecules with functionalized end groups that are specific to, say, metal cations. Okay, the idea is it's a continuous ion exchange process. So you don't have to go through some of the difficulties you do with a batch mode ion exchange. Basically, the system works a lot like a lawn sprinkling system. If you can imagine that, that's about how sophisticated it is. You would mix these particles with a leach solution or maybe some mine runoff that has rare earth elements. Metal cations are going to adhere to either just the raw magnetite. It works pretty well as an adsorbent just by itself, or maybe with one of these ion exchange particles. Well, then it goes through a reactor that's somewhat proprietary that we've developed, and that basically has an electromagnet in it. It grabs these particles, so that's the continuous aspect of it. The solution flows through, and so it's continuous, but we're able to maybe take that line offline, de-energize the magnet. Well, first of all, change the valve position, de-energize the magnet, wash the particles off, and then we can strip the particles. We've shown that. And with things like copper and zinc, we can electrowin. We can build a solution tenor up sufficiently. We can electrowin. Electrowinning is just not in the game for rare earth elements because they're so reactive. It's just not practical, at least not in an aqueous system. So we have high hopes for this. The idea here is hopefully we're going to be able to come up with a selective adsorbent for the different rare earths. Okay, the next project is Richard Ledusser again, and this time he's teaming with Scott Cogill, and they're looking at novel separation techniques for rare earth elements using what they call a resonant vibratory separation system. Essentially what they plan to do is, again, they're looking for ways to more efficiently collect the rare earths, but also if there's an opportunity for selective collection, they're going to be looking at that. And essentially what they're going to do is have an adsorption swing reactor mechanism set up to do this. So basically it's rare earth separation that they're looking for in this particular project. Okay, the next project is one that Courtney Young, and he's teaming with another of my colleagues at Montana Tech, Dr. Avamanyu Das, and they're looking at the advanced recycling of magnets and batteries. And this is an instance that maybe is a little bit different than what I was saying earlier. At least here with magnets, the rare earths are already concentrated. The difficulty is separating them. So what they're looking at is basically a molten salt or fused salt process to solubilize the rare earth elements. In this case, we're talking about neodymium, and then affect recovery of the neodymium. And if that's successful, then they envision other applications of this technology, things like cobalt samarium magnets, nickel metal hydroxide batteries, things like that. Okay, so the last task number 14, is actually based on a discovery in Jack Skinner's laboratory. Dr. Skinner is the head of the mechanical engineering department at Montana Tech, and his research associate, Dr. Andriolo, and also Dr. Katie Haler, who's the head of the chemistry and geochemistry department at Montana Tech. They were concerned actually with the CFMR system that I described earlier, if there's some kind of an accidental release of these particles, particularly the ones that have the magnetite encased in silica and the organic molecules with the function end groups attached to it. They're worried about environmental insults that might happen if that was accidentally released. So they looked at it, and actually they've come up with kind of a novel, or a very novel particle, where what they're doing is coating the magnetite with titanium or titania functionalized hydroxyapatite. And what that does, that much less toxicity. There, part of what Katie Haler did is look at the toxicity of these particles versus some of the other particles that I mentioned. They didn't look at raw magnetite, however. The exciting thing about it is these particles actually have really good adsorbent qualities. So they have pretty high loading rates. In fact, very high loading rates for things like rare earths. And another exciting aspect of it is they've done some preliminary test work that indicates that these particles may show some selectivity for rare earth element adsorption. So anyway, this was going pretty rapidly. It's kind of like one of those things, see Europe in 3 days. So hopefully I didn't talk too rapidly, and just gave you a little bit of flavor of what we're planning to do here in the next 5 years. So again, thank you for your attention.
Questions for the crew?
Is Tech and the Montana Bureau of Mines working with any of the surrounding states on some of the rare earth and critical mineral minerals applications. So I know in Wyoming, the Wyoming State Geological Survey and UW are also looking into techniques in identifying these locations, at least in Wyoming, that may actually cross state lines.
Okay, I can give you my short answer, and then if either Ron or John want to chime in, I'm not really a spokesman for CAMP or for the Bureau. But I can tell you that I've got 4 active rare earth element projects going on, if you include this upcoming one with the Army. So, yeah, some of them I'm involved with, and the Bureau is also involved in some work that we're doing with the University of North Dakota. And then I've also done work with rare earth elements from deposits in Wyoming. Do you guys have anything to add? Or okay.
Other questions?
There was some maps shown pretty broadly across the state showing moderate to high potential areas. I was just wondering how that was determined.
Yeah, I think I understand your question. Yeah, I mean, the green areas on the map, there were a lot of wilderness study areas done and general, mineral potential studies done late 60s, early 70s, in the mid 70s. And so these were compiled by U.S. Bureau of Mines and U.S. Geological Survey. What we've done over the years to produce a map like that is basically go back through those. High in mineral or even low potential is defined by each one of the studies, of course. So that map just represents kind of a generalized areas that were identified by one publication or another as high or moderate. So I hope that answers that.
Other questions?